Chapter 9 Ray Optics and Optical Instruments. Nature has endowed the human eye with the sensitivity to detect electromagnetic waves within a range of electromagnetic spectrum. Electromagnetic radiation belonging to this region of the spectrum is called light. So it is that part of the electromagnetic spectrum which produces sensation of vision in human eye is termed as light. The wavelength range is from 400 nanometer to 750 nanometer. So those rays whose wavelength ranges between 400 nanometer to 750 nanometer produce a sensation of vision in human eye. Now there are two things that we can intuitively mention about light from common experience. First, it travels with enormous speed. The velocity of light is enormous. Second, it travels in a straight line. That is, the photons travels along a straight line. This is what is called the rectilinear propagation of light. The speed of light is finite and measurable. The accepted value is 2.99792458 into 10 to the power 8 meter per second. For practical purposes, we have approximated this value to 3 into 10 to the power 8 meter per second. And this is the highest speed attainable in nature. No material body can have a velocity greater than that of light. A light can be considered to travel from one point to another along a straight line joining them. That is, from an object A or from a point A to another point B, light travels along a straight line, and that is called the ray of light. A bundle of such rays are called beam of light. We can have many types of beam of light, like a parallel beam of light, a divergent beam of light, or a convergent beam of light. So parallel beam of light means the light coming from a faraway object seems to be parallel. Divergent beam of light means light diverges from a point. For example, if you light a torchlight, you can see how the light comes out. It comes out in a conical shape. So it diverges in that fashion. In the similar way, you can also converge light to a point. So in this chapter, we consider the phenomenon of reflection, refraction, and dispersion of light using the ray picture of light. Using the basic laws of reflection and refraction, we shall study the image formation by plane and spherical reflecting and refracting surfaces. We then go on to describe the construction and working of some important optical instruments, including human eye. Let us see reflection of light by spherical mirrors. When a ray of light is incident on a smooth polished surface, a reflecting surface, the light ray bounces back to the same medium. This phenomenon is called reflection of light. That is, the photon or the light bounces back to the same medium is called the reflection of light. Here you can have two medium 1 and medium 2, and let us see what this reflection means. An incident ray gets reflected. That is, the ray gets bounced back to the same medium, and this is what is called a reflection of light. Now let us see the laws of reflection. That is, the laws governing this phenomenon, that is reflection. See the ray diagram explaining reflection of light. The first law is the angle of reflection. What is angle of reflection? The angle between reflected ray and the normal to the reflecting surface as indicated in the figure. There is theta. The angle of reflection equals angle of incidence. Now, what is angle of incidence? The angle between the incident ray and the normal. That is, the angle of reflection equals angle of incidence. This is the first law of reflection. The incident ray, reflected ray, and the normal to the reflecting surface at the point of incidence lie in the same plane. That is, the incident ray, reflected ray, and the normal. All these three lines lie in the same plane, and that is the second law of reflection. These laws are valid at each point on any reflecting surface, whether plane or curved. That is, it is applicable. These laws are applicable to any reflecting surfaces. Now, another important aspect, that is what is called the sign convention, how we can measure various distances. To derive the relevant formula for reflection by spherical mirrors and refraction by spherical lenses, we must first adopt a sign convention for measuring distances. Here we make use of Cartesian sign convention. Now, what is Cartesian sign convention? Let us see. According to this convention, all distances are measured from the pole of the mirror and optical center of the lens. You might have learned the pole of a mirror and optical center of lenses in very small classes. So the distance that we have to measure, it should be measured from the pole of a mirror or an optical center of the lens. The distances measured in the same direction as the incident light are taken as positive, and those measured in the direction opposite to the direction of incident light are taken as negative. That is, the reference direction is taken to be the incident light direction. All those distances that is measured from the pole, and if you go opposite to the direction of incident ray, those distances are to be taken as negative and the other to be positive. The heights measured upward with respect to the principal axis are taken as positive, and those measured downward to the principal axis are considered to be negative. Now let us see these laws pictorially. Here you could see a mirror and its pole. Incident light is from left to right. That means the object is on the left side. So that is the direction. From left to right, it is taken to be positive. So if you want to measure the distance of the object from the mirror, you have to measure it from the pole. You have to start from pole and has to go opposite to the incident light. That means the object distance is taken to be negative. Now the height upwards from the principal axis, you could see an x-axis there, and that is actually called the principal axis. So if you measure heights upward, they are taken to be positive. Those measured downwards are taken to be negative. Now, focal length of spherical mirror, another important aspect. For that, let us see what happens. A parallel beam of light is made to incident on a concave mirror and a convex mirror. When paraxial rays are made to incident on concave mirror, paraxial rays means those rays which makes very small angle with the principal axis, or those rays which will be incident at points which are very near to poles of the mirror. Such rays are called paraxial rays. The reflected rays converges at a point on the principal axis of a concave mirror. That is, when paraxial rays are made to fall on a concave mirror, then after reflection, these reflected rays will be converges to a point. They all passes through a point on the principal axis, and that point is what is called the focal point of the concave mirror. Here you could see a concave mirror, and the dotted line represents the principal axis. Now let us see. P is the pole, and if Paraxial rays are made to incident, all of them gets reflected and they passes through a common point F on the principal axis, and that is what is called the focal point of the concave mirror. Similarly, in the case of a convex mirror, what happens? Let us see. After reflection, those reflected rays seems to be coming from a single point F on the principal axis, and that is termed as the focal point of convex mirror. The point F is called the principal focus of the mirror, and the distance between the focal point and the pole is taken to be focal length of the mirror. If the paraxial beam of light were incident making some angle with the principal axis, the reflected rays would converge or appear to diverge from a point in a plane through F normal to the principal axis. That plane is called the focal plane of the mirror. This is called the focal plane of the mirror, and it is demonstrated or that is shown in the figure.